Yes.
All right, Gabby, we have another box, and do you want to do the honors?
Yes.
And while you're opening that, do you want to tell people a little bit about what you do?
Oh, yes. So I just started school at the University of Nebraska-Lincoln. I'm in a PhD program for microbiology, and I work with Dr. Carrie Weber. And I'll be doing something astrobiology related. And my project will be astrobiology related, and bioenergy related, kind of. I also work for the Agnostic Life Finding Association. It's a nonprofit, and we are looking to send our instrument to Mars to detect life before humans arrive there and potentially contaminate the surface. Or not potentially, they will contaminate the surface.
Yeah.
If they get there. When they get there. So yeah, that is what I do.
Oh. So what made you interested in aerospace? You didn't know you were going to be impromptu
No, I
interview,
did not.
did you?
No, but I appreciate the spontaneity of it. I was interested in microbiology. I started as a microbiologist, and I always enjoyed space. It was more of like a hobby for me. And then once I got to college, I kind of realized that I can combine the two, and I started to. There we go. It was a tough one. That's kind of when I combined the two, and I found out about astrobiology, so I kind of invested myself in the community. I did work with Dr. James Holden at UMass Amherst. I worked in his lab, and he works on organisms that live in hydrothermal vents. So yeah, that was kind of my introduction to it, and I really enjoyed it. And then I wound up doing like an internship at Blue Marble Space. I did their Young Scientist program, and I actually did an REU with Carrie Weber at the University of Nebraska-Lincoln.
Can you tell folks what an RU is?
Yes, an REU is a research experience for undergraduates. So, a lot of those are sponsored by NSF. I know about NSF because that's kind of my sector, but I think the FDA also sponsors some. There's a bunch of places that sponsor them, but it's specifically an REU, and it'll be like a summer program where you go to a university, and it tries to prepare you. Like, you do research in a lab, so you get to, determine if you want to do research or not. But it also tries to set you up if you wanted to go to graduate school after your undergraduate degree, which they got me. Here I am.
That's pretty awesome.
Yeah.
Thank you for sharing that,
thank
Gabby.
you. Thank you for asking.
Absolutely.
Here is your
wow
box of files.
So indeed, the label was correct.
I'll turn it this way so you can kind of see the labels of what the boxes say, or the files say, rather.
Okay.
So we have MSA, ion source and heater, the corona, ion pump, MS, performance and background. Sorry, I realize I can't read upside down. I don't know why I'm trying to do that. MS failures, MS technical manual, the PPU, the IEA parts and modules, the IDS, PCS and inrush current, the SN 2 and 3 specific, the
serial
power
numbers, yeah.
Yeah, the power reports and the vibration and thermal tests.
So what should we pull out of there? What do you think looks interesting?
You know what I think is kind of interesting?
Yeah, what's up?
Stuff about the MS. So maybe the performance and background, or maybe the failures might be cool.
Ooh, should we look at the failures?
Yeah, I think
okay, let's look at the failures. You can do the honors.
Okay.
It's all you. Dun, dun, dun.
I'm not entirely sure.
Where the beginning and end is?
Yeah.
Yeah, so it's usually like what I typically just sort of put a finger in front of and a finger in back and then try and grab it out, but it's not gonna lie, it's not easy. These are well packed. There you go.
There we go.
You got it.
Actually, the smallest file in there.
Yeah, well, that's a good thing.
That's pretty funny.
Let's close this up and give you an ad hoc desk. Actually, let's leave it like that.
Okay, yeah. Welcome to my desk. I'm also matching with the file.
Nicely done. Well coordinated.
Yes. Okay, Viking GCMS program design file memo. So, that's a pretty funny note. Did you read it?
I know. What does it say?
Pages 54 through 69 give no comfort that PE knows anything about HV design.
Okay.
Interesting.
So,
Coming out swinging.
yeah. So that's interesting. So PE stands for Perkin-Elmer.
Mm-hmm.
And all of these different instruments, every little piece of this was designed by a different OEM, original manufacturing, of different kinds of parts. I mean, from screws to plates to specifically designed wires that had to survive both high temperatures of atmospheric entry, and low temperatures of the surface of Mars. Every little bit had to be called what's called flight qualified. And so it's true. Honestly, PE wouldn't know anything about HV design because this literally was the first time this was being done.
Yeah.
But it is kind of funny because we do see notes like this throughout our curation process.
Very passive aggressive.
So, yeah. So we do get these kinds of notes, and we have to, before we actually enter into this, we have to talk a little bit about the context, right? So you have a program that's doing something for the first time, going to the surface of Mars, and a whole lot of people that are telling you that you're going to fail. Like, lots of people are telling you that you're going to fail. So the incredible pressure that these engineers and scientists were under to design everything right was absolutely intense. And so there were times when they would get parts provided by one vendor and it wouldn't be adequate. And they'd have to go back 4, 5, 6, 10 times. And sometimes it reached a point where they would be, well, we can't use this vendor anymore unless they improve their testing and qualification. And so we're going to go over to talk to this other vendor over there. And so they go and talk to another vendor. It didn't happen a lot because you really want to do things with the same organization as much as possible. But it did happen every once in a while. And what that really did was it upped the game. So at the end of the day, the thresholds within which these scientific instruments were required to meet were microscopic. I mean, microscopic is not the right word because that's visual, but the thresholds were tiny for some of these things. The data couldn't be greater than 0.002 or 0.0002 in some cases. For example, with the seismometers and meteorology instruments, same thing with the GCMS. They had to have really, 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 really accurate data. And so this is part of the process, right?
Yeah.
So back to the document.
Should we?
So this is from Perkin-Elmer Aerospace Division. And this particular memo was about the failure analysis of the PTC failure and qualification position report. Do you want to read what
Sure.
they said?
Yeah. So it says, with the PTC failure occurring at the same time the qual system was being firmed up, the design approach for qual and PTC obviously was impacted. The failure history and assessment of the electronic and filament failures and the resultant failure and analysis. Nope, there's no and, just analysis. Tear down and scheduled rebuild cycle have all contributed to the design and manufacturing approach that engineering considers should be implemented on qual and subs. The changes include ion source filament spring cracking, MSHV headers, encapsulation failure analysis, test results and proposed solution, terminal board additions, and filament failure analysis. In each case, there are recommendations made to solve the aforementioned problem.
So this is back in 1973. So this would have been 2 years before launch. In fact, almost exactly 2 years before launch, because it's August of 1973. And so they had 2 years within which, well, they didn't have 2 years. They had probably 9 months to maybe a year to solve these problems. And then all the integration testing had to happen. And then things would be shipped, they'd be integrated and assembled, and then actually heat sterilized in ovens, the entire spacecraft, prior to going down to the KSC for launch. And then again, some sterilization happened down at KSC, and then loaded into the Titan 3E Centaur, where the spacecraft lived during its travel to Mars from Earth. So less than 2 years to figure out these failures. So pretty cool. Okay, what's next? What's inside?
So let's see. So just Viking position report for qual hardware and PTC failure analysis summary. So August 6, 1973. Can I say who it's prepared by?
Sure.
So it's prepared by R.J. Zollinger, R. Wayant, K. Bellata, and G. Voorhees.
Yeah.
Oh, that's a cool last name.
Yeah.
So just a table of contents talking about, so the GCMS MSA electronics configuration differences, mechanical configuration differences, the ion source filament assembly, the MS high voltage headers, the delimitation of Dow Corning silicone materials 93500 and 96083, the tabulation of tests conducted, the corona failure, terminal board addition, PTC electronics failure analysis report, and events preceding PTC filament failure.
All right.
So, and list of there's some illustrations too.
Yeah.
Cool. So I'll kind of
If you want to rotate that
switch
carefully.
the position a little bit, so I can kind of see how it's
Can you
formatted.
see that a little bit?
I think. How about if I do that? There we go.
Okay. So the PTC is one of the test modules, and the DTU is another part of the test, but I can't remember what that acronym particularly is. I'll find out, and we'll let you guys know later. We'll put it in the notes.
Yeah. So I guess then it has like a, so it has a little report. So it talks about the statement of the problem, and it talks about the discussion.
So after they discuss the problem, my guess is there's probably going to be some recommendations. Yep, solution of the problem.
There you go. Yeah. Solution.
Yeah, and some steps that can be taken during the solution. And
Oh, how cool!
nice.
There you go. There's one of the illustrations.
Yeah. So I think we saw this in one of the other videos. For those of you that haven't seen it, there's another video out that has actual photographs of these test units, and that looks kind of familiar to some of the parts that we were looking at. So.
Yeah, absolutely.
And we'll be scanning each of these pages. So Gabby is going to be here working all week curating these documents. So once these are scanned, we'll make them available to everybody. Now this is pretty wild. Look at that. Wow.
Yeah, it's the
That
PTC
is
filament assembly.
A filament assembly. So that is a tiny, tiny, oh boy. It's hard to even describe how small some of the things that are measured and how accurate they had to be to make things work. So 87% of the wire diameter, both filaments were subjected to power inputs. I'm looking for something that tells us the size of the wire, because everyone's, 0.0045 inches.
Yeah.
That's pretty wild.
Very small.
Yeah. Okay, we've got another one of statements of problem and discussions and solutions. So a lot of these things, if they weren't too severe, they were solved and then they moved on. But for some of the things that were critical to the entire success of the mission, they were put on what was called the top 10 list by Jim Martin. So Jim Martin would make the decision with the scientists. Chief engineer is Tabak, and chief scientist Jerry Soffin, as to what would be on the top 10 problem list. And I'm not certain if these were, but there were a lot of details that were on there, and then when they were resolved, they would move off the list and move on to another things. But one of the things that was really exceptional about the way that this program was managed by Jim Martin was that he organized the mission so that it was all about eliminating failures as opposed to demonstrating success. And so if you focus on rewards and success models, people can say, oh yes, it worked great. But if you work on eliminating failures, then what you do is you dig deeper into the things that are not working right, with the understanding and acceptance that failures are expected, and then you work hard to fix what those failure items are. So whereas at one point NASA said, and other people have said, failure is not an option, during the Viking program, failures were sought out and eliminated, and that's one of the reasons why the mission was so successful.
Bunch of illustrations there.
More illustrations.
And then maybe I can't really
Protective
read from
cover. But yeah, it is hard to read. When we scan them, it'll be easier.
Yeah.
So, and all of this material will be scanned at high resolution and be made available. You can look at hashtag VMMEPP and our website, the Viking Mars Missions Preservation and Education Project is our organization, and the Viking Preservation Project.org is our website. So all the material will be available there eventually for perusing by anyone for free. So now this is interesting. So EIMAC Division of Varian. So that would be another company that actually worked on the mission. So that's pretty cool. We're always looking for different manufacturers that actually provided small elements of the mission.
Right.
So. So does any of this remind you of the instruments that you've seen that you guys are working on integrating with for Alpha?
Sort of. I mean, our instrument looks a little bit different, but yeah. But some of the components, it's funny to see like the drawings here, and then see kind of the drawings that we come up with, or even look at our instrument and be like, this is what it looked like at one point, right? It was just pen and paper. And to see what that can become is just incredible.
Is it helpful to see how other things are organized, how information is organized and testing is done and things measured at all?
Yeah, and it's always so interesting to me, because part of like when you're building something, right, or trying to test something, like that's not even the hard part. The hard part is how do you organize all the data that you're getting from it? Like that is always the worst part, right? Because sometimes it's pretty easy to get things to work if you know what you're doing, but so it is kind of helpful to see like how all of this is organized and like how detailed they were. And I'm sure when you start to really read and go through all of this, it's still not enough detail, like
there's always more that we wish
more.
We could do if we had bigger budgets and longer windows.
And there's always more that we could be writing down for future that in that moment you think, oh, it's fine.
Yeah. Well, one of the things that Viking was known for, to the dismay of many scientists and engineers, actually, was the amount of documentation on everything.
There is a lot. Yeah.
There's a lot of documentation. What have you seen since? What surprised you the most when you came to our archives?
There are many boxes. there are many boxes. There are multiple rooms of boxes, but I mean, even within the boxes, right? It's not just one thing in that box. It's like this box, right? There's a few files, but within all of those files, there's like hundreds of papers. So it's definitely a lot of sifting through. It's a big task to go through everything and to scan everything. But it's really rewarding. Like a box that we opened earlier had a bunch of photos, and that was incredible.
And for test engineers who are doing instrument design, this is the kind of material that would be really, really valuable, especially the failure reports, because then if they discovered that a certain kind of valve or lubricant didn't work well at X temperature, then all of you who are listening, who are designing instruments, can learn from the things that didn't work right on, and that did work right on Viking, to say, oh, well, we've used this material, this worked well, this didn't work well. And that's really part of the purpose of all of this, is so that all of you guys can learn. And also, it's just pretty darn interesting.
Yeah. Just a lot of reports.
So this is really interesting, material science here. So I'm always telling people that material science is one of the coolest sciences that you can study, because it really brings engineering and science together. There are instruments that can't be used as containment modules for regolith, because if you end up with certain mineral elements that are in contact with those particular materials that are containing them, what happens?
They'll react.
Yeah. So have you seen that in any of your work?
Sample. I don't work hands-on with the instrument, so I can't really talk to our instrument, but I mean, I've seen that before with other things in my labs, where you have to be really mindful of what chemicals you're using. Because sometimes you even get like false results, right? Sometimes it might be a positive result you're getting for something, and you're like, oh, that's great. But when you look back, you kind of realize, oh, I didn't understand that there was a chemical reaction happening, and that kind of led to something else.
So when you say chemical reaction, what are some of the other words that like are used when, say, metals interact with gases or other
Like oxidation.
materials? Yeah.
Yeah.
So like oxidation, leaching,
Yeah.
stuff like that. So those are terms that you might hear on Earth, and you see a beautiful old roof of a house in some area, and it's kind of turned green, and it was copper, and it oxidized, and so many things like that. So some of the words that you use in science, what are some of the other words that we use for that, for chemical reactions?
Oh goodness.
I mean, like when you put two solids together, sometimes people don't think that that's a chemical reaction, right? A lot of people think that chemicals are things you pour, like liquids, you know what I mean? So there's a lot of misunderstanding.
I mean, even like water boiling, right, is a reaction of a sort because it's changing phases. Like when you have water, it's liquid. When it's boiling, all that vapor is really gas.
Exactly.
But maybe not gas, but you know what I mean. It's vapor that's being released in the air into the gas form.
So when something transitions from one thing to another, when it comes into contact, that's actually a chemical reaction.
Yes.
And that's something that a lot of people don't know. So, fun fact.
Absolutely.
So ceramics were used, metals, plastics, and rubber.
And it's cool to see the different variety of materials that they use as well.
Yeah. And some of these, like, so Bakelite, that was actually used a lot starting in the 1920s for the telecommunications, in the telecommunications world. So a lot of the resistors that they would have around wires, I don't know what the words are called, but some of the things that you would see containing different electrical things and currents were Bakelite. Kind of cool. So yeah. Plus, a lot of retro art was made out of Bakelite.
I haven't heard of Bakelite, so.
Oh, interesting. Okay, yeah. Yeah, I think it was
or maybe I did know about it, but I didn't really know what.
It probably has another name now. This probably goes by another name now. So Dow Corning was obviously involved, and one of the things that they became known for that actually bumped them up in the technology world was silicon.
Yeah, this is space grade materials.
Yeah.
Oh yeah, what is this? What does that word say? Can you read that or no?
Formation.
Oh,
information.
Oh. I was like, it's an Asian. Ends in that.
Information about silicon.
Yeah, there you go.
And so this is when silicon was really becoming more broadly used. So think about it. Everything we do, like you can go buy a pot holder today that's made out of silicon.
Yeah, a lot of stuff.
Or a dog water dish that you carry in your backpack, right?
Yeah.
Those are made out of silicon.
Yeah.
But it's common today, but back then it was really not known what are all the different uses for silicon.
All my kitchen stuff is silicone.
Yeah, right? And silicon has actually been looked at as one of the new building blocks for life. So, yeah, that's pretty cool. All right. Awesome.
I don't know if you want me to get to the
I don't know. Let's just see. Is there anything? What else is in there? We can flip quickly through there.
Yeah, it's just a bunch of reports, and then just
some little schematics that measure things where they should be.
Yeah.
All right. Cool. All right. Well, thanks you guys for listening. Again, Gabby, do you want to introduce yourself for those that didn't meet you earlier?
Oh, yeah. So I'm Gabby, and that's it, right? I'm Gabby. I am a first-year PhD student at the University of Nebraska-Lincoln, studying microbiology, but it's more like an intersection of geomicrobiology, astrobiology, bioenergy. It's kind of those topics. And I also serve as the CFO for the Agnostic Life Finding Association, and we're looking to send an instrument to Mars to detect life before human arrival. And we want to also protect whatever native Martian life might be there.
Yeah. And Gabby has generously offered her time to curate with us and explore these boxes. So thanks, Gabby.
Thank you for having me.